Okay.
So Chris Wood is the technical lead of experimentalist tools in the quantum software group at IBM Quantum, where his team develops software for calibration, noise characterization, error mitigation, and simulation of noisy quantum computers. Chris received his PhD in physics, quantum information, from the Institute of Quantum Computing at the University of Waterloo, Canada in 2015, and joined IBM in 2016. He has been heavily involved in the open source development of Qiskit since its inception in 2017. Currently, he leads the Qiskit experiment and Qiskit Dynamics projects, and previously he led Qiskit Air, Qiskit Terra, and quantum info development. And also, from my end, when I was in IBM Watson Lab, like from last year to some part of this year, Chris was my supervisor. So thank you so much for agreeing to give this session. So on to you.
Thanks, Ritaji. I guess I should just give one correction. I didn't lead the Qiskit Terra development, just the quantum info module part in Qiskit Terra.
Oh, okay.
Yeah, there's a lot of other things in Terra that I didn't touch very much. Okay, so I was mostly going to go through just some examples in a notebook today. I don't know if people can ask questions about specific things they're interested in or not, but I'll just start with a quick recap of what we're trying to do in the first place with simulating noise. So basically, we've got a mathematical description of open quantum systems that describes noisy quantum computers. So we have the states of the system are represented by density matrices. I can maybe make this larger. Gates are represented by quantum channels or completely positive trace preserving maps, which are basically maps that map density matrices to density matrices. And measurements are represented by some positive operator valued measure that can take density matrices and return a set of probabilities from which you can sample measurement outcomes. And so there's a variety of tools in Qiskit to simulate and work with these, work with state operators, work with different types of quantum states, types of quantum channels and other operators, measurement errors, and do simulations. So if you're not familiar with it, there's a lot of tools in the Qiskit quantum info module to do this. So classes to represent operators, so like unitaries, Pauli's, and things like this. For noise, there's a special set of operators to represent working with the different representations of completely positive maps, these channel classes. So things like Krauss, superoperators, Choi. These are all equivalent but different representations of the same mathematical object. And using these, you can switch between them quite easily, depending on what you need. There's classes for states, so like the state vector and density matrix, for example, which you can use to compute properties of these, like fidelities, evolve them by channels, and do partial traces and things like that. And then these helper functions to do some of the things I mentioned, like partial trace or compute fidelities, purities, etc. Generate random states and channels and things like this. And then on the other side, I should mention that technically a lot of these classes are simulators as well. So when you have a density matrix and you evolve it by operators or channels or circuits, you're performing a type of simulation. So that's one way you can do simple sort of noisy simulations in Qiskit. And then for more complicated or advanced stuff, there's Qiskit Air as a simulator, which has itself a bunch of tools for defining noise models for circuits and running them and evaluating them that then you can run on things like HPC clusters. So if you haven't seen them before, there's a few tutorials on these for Air. These are a few years old now, but they're still mostly valid and a good starting point. So there's the tutorial just on the simulators in Air, which kind of explains, why won't this scroll? Oh, it seems my web browser crashed. One second. going on? Let me restart this. Try again. Here we go. So there's a tutorial just on the basics of using Qiskit Air, so the kinds of simulators that are involved in it. Running different Air supports a bunch of different simulator methods like state vector, density matrix, can also simulate super operators and channels directly. I'll show some of these things. So yeah, this is a good starting point. Then there's a couple of tutorials on working with noise models that go into a fair bit more detail than I will in this session for how you can construct some of these. So these are all in here in the tutorial section of the Qiskit documentation under classical simulators. So the device noise model, building noise models. The device noise model is basically a built-in noise model that we can use as a starting point that's very simplistic. I'll describe a little bit. And then you can build your own very customized ones to do whatever sort of research task you'd like to do, which this tutorial goes through. So if I close them now and work on this, let's hope it doesn't crash again. So if we start with just the mathematics of a noisy quantum gate, so there's I mentioned various representations. You can write these as a common one is the Krauss representation as a set of these matrices K. And so the most simple example of this is something like a bit flip error, where say with some probability I do a gate I want. Well, I guess in this one I phrased it as I'm actually trying to do an X gate, but with some probability I do the incorrect gate. So this looks like some mixture of the gate I want with some probability and some gate I don't want, in this case the identity. And how I would represent things like that. So if I import the quantum info module in Qiskit, I can build this Krauss channel by specifying the matrices. So if I want to just write this as a list of the matrices here, this set square root 0.9 and x and 0.1 I can do that using some of these classes like shown here. So I create a matrix, so this could be a NumPy array, but I use these operator classes just to easily make an identity in an X gate without having to type out the matrix. And then I can construct this channel object. And now I have a channel. This is a class with various methods. So is it a CPTP channel, for example? In this case, it is. You can do things like compute the process fidelity of it. You can change the representation of it. So to go to, say, a super operator, I can just initialize the super operator class with this and it will transform it. A Pauli transfer matrix or a chi matrix. So all these different ones can just be done by calling these classes, which will perform these transformations. What I can't do is transform it back to an operator because it's not an operator, it's more general. So this would try and transform it back to a unitary matrix, which can't be done because it's not a unitary channel. You can also work with these objects. There's an API for operators in Qiskit for composing them and performing tensor products and powers. So I can do things like take the power of the channel to repeat it a bunch of times. I can perform the tensor product to make bigger channels. I can compose it or do the dot product and work with these like mathematical operations. And then with the density matrix, so I can do the same thing with states. I can define a density matrix from a NumPy array. I could also initialize it from a label like shown here. I could, put in, you can basically use the different Pauli eigenstates represented as 0, 1 for z, plus minus for x, and right and left for y. Whoops, I can't evolve it. So I can make a density matrix like that. And then to evolve it by a channel, this is a 1-qubit channel, so I'd have to specify the qubit I want to evolve. So I can apply these operations. If it's the same size, you can just call evolve. Another thing you can do is, well, this is for circuits. Let's see if it works for a channel. No. Yeah, I'll come back to that. And so you can do a lot of sort of the kind of calculations you might do with pen and paper for working with a small number of operators and states and things. The idea is you can do them numerically with these classes and compute quantities, fidelities, and things like that from them. And then for more complicated things, when you want to start working with larger quantum circuits on multiple qubits, that's when we kind of turn to simulation. And now one thing to keep in mind when working with these objects is that quantum simulation is exponential and very expensive to simulate it classically. So, there's a limit to what you can do, which is, of course, why we need quantum computers. But it's something worth keeping in mind when you're doing this and trying to think of how long things might take to run. So if you think about an ideal simulation of a state vector, that has 2 to the n complex numbers, each of which is 16 bytes. And so you need some amount of memory that scales exponentially to represent that state vector. When you go to a density matrix, you need twice as much memory for the same number of qubits because you have 4 to the n now complex numbers you wish to store. And if they're double precision, again, 16 bytes each. And then if you try to simulate a channel, so the super operator as a matrix itself, rather than its action on something, this doubles again. So now you need 16 to the m complex numbers. So basically, I think it's roughly like you need something like, I can't remember exactly, 32 gigabytes of RAM for around 31 or 32, 30, 31, 32 qubits. So for that same amount of memory, you could do 16 qubits as a density matrix or only 8 qubits as a super operator and use all your memory. So because of this requirement of density matrices taking twice as much memory, an alternative you can do for simulation to do more qubits is this quantum trajectories approach, which is basically a mathematical trick to unravel the evolution of a quantum channel on a density matrix by applying it to individual pure state state vectors and then averaging over a ton of those trajectories to approximate the final density matrix, which is the average as the number of samples goes to infinity. And the trick to do this in simulation requires the Krauss representation of a channel. So if you have a super operator or a Choi matrix or something, you convert it to a Krauss channel. And then what we do is we treat the set of Krauss matrices like a distribution that needs to be sampled from. And this distribution is state dependent, unlike with unitary. If the Krauss matrices are all unitary, so it's a mixed unitary channel, then unitaries preserve probabilities. So you know the probabilities ahead of time. They're kind of the coefficients in front of the unitaries. But for an arbitrary Krauss matrix that might not be a mixed unitary channel, you don't know this. So you have to basically compute this probability distribution from the current value of the state in your system. So every noisy gate, you have to take the state at that time, compute this distribution to sample from, and then you sample a single Krauss operator to apply and apply an update by applying the non-unitary Krauss, which will typically decrease the norm of the state, and then you have to rescale it by the amount it was decreased, which is the square root of this probability. And so when you do a trajectory-based state vector simulation with a noisy channels, what you're doing is at every noise process, you're sampling one of these Krauss terms and projecting, and then projecting and projecting at every noisy instruction. And then at the end, you average over all the shots to get some counts or maybe some probabilities or a approximate density matrix. And so what does that look like? So if I just take the very simple example now, so I import the air simulator. I'm going to build a quantum circuit, so one thing I should mention is these noise operators and channels, you can just add them directly as instructions to quantum circuits. They won't be able to run on a backend anymore because they're not a valid unitary for a backend, but they'll run on simulators and these state vector type classes, density matrix classes. So I create a channel with just this Krauss instruction I made before, and then I add an air-specific instruction to save the density matrix. So rather than doing measurements, I just want the simulator to return the final density matrix. And then if I run this on a density matrix simulation in air, so I set the method to be density matrix, I get back some density matrix that should be the same as the one I got up here using the built-in simulator from the density matrix class that just uses NumPy. And if I want to compare that to this trajectory approach, so I could run the same thing on a state vector now, where now I need to specify the number of shots. And if I do say like 100 shots, I might get some number, but that's going to change every time I run it because it's sampling basically from this Krauss distribution. And as I increase the number of shots, this distribution on average should get closer to this one, but you might have to do a lot of shots to get it to be very close. And of course, the trade-off here is you use less memory, but you use more time, potentially, depending on your number of shots, because on average, because there's twice as much memory in a density matrix, each instruction takes twice as long to update the state. But if you have to do more shots in the state vector to get a good average, then if you have the memory, it might be better to do a density matrix simulation. And so by default, if you don't specify a simulation method in air, it will do one of these simulations. It'll basically have some heuristic for choosing the simulation based on whether the memory requirement is the number of shots and the memory that your circuit needs. So I don't need all these other cells. Yeah, and as I mentioned, from a simulation point of view, if you're doing general Krauss errors with a state vector simulator, the simulation is going to be slower than if you're doing a mixed unitary simulation. So if you have something like a Pauli channel or some channel that's a mixture of unitary errors, this is faster to simulate even with the state vector approach because you don't have to do this extra sampling, this extra computation of computing probabilities, which is an expensive operation if you have a very large state because you have to iterate over the full state vector. So Krauss simulation can be like 2 or 3 times slower than unitary noise simulation because of this. So that's something to keep in mind. Now, the next thing is measurement. So generally, a general measurement can be written by a POVM. In Qiskit Air, we don't exactly support the most general kind of measurement of an arbitrary POVM, but we support basically two kinds of errors you can add, which still gives you a fair bit of flexibility. So you can have a quantum error before the measurement, which is any of these CPTP maps you can apply before a measurement, and then you perform an ideal measurement. And then you can also apply a classical readout error, which is after your measurement, you perform an ideal measurement, you get some sample bit strings, and then you basically resample them based on some classical probability distribution of those, which is specified by something like this, and then return that sort of resampled probability distribution of bit strings. This is sometimes also called an A matrix type model for readout errors. And it's often the model that's assumed when you're doing readout error mitigation techniques in a lot of them. So now that I guess that's a crash course in in channels in Qiskit. So how do you work with these? So basically, if you want to do noisy simulation, there's a variety of things you can do. So you can build circuits, say for your application. If you want to be very, very customized about what noise you have, you can design, engineer the channels to be exactly what you want, and you can insert them like instructions anywhere you like in a circuit, so that you can completely customize your noise model that way, under the assumption of it being a Markovian noise model that can be represented by these CPTP channels. So you can put in your gates in your circuit and put in your channels wherever you want them, and then you can run that on the density matrix class or with the Qiskit Air simulator to do a noisy simulation. The other approach you can do is you could construct a transpiler pass to do this automatically. So given an ideal circuit, you could transpile it, and that transpiler pass could, like usually transpiler passes are doing things like optimizing gates and mapping, C0s between qubits that are actually coupled on a device and things like that. You could also write transpiler passes to insert noise in your circuit based on the type of circuit or the geometry. And so there's actually a couple of transpiler passes to do that in air. So this local noise pass and relaxation noise pass. The local noise pass, you can basically define a function which will, it's kind of like a mapping where you can specify instructions and the qubits they apply on, and then you can replace it with any other instruction you like, or append it with noise or prepend it with noise. So you can use this to build local noise, so local being noise that affects only the same qubits as the instruction that's noisy. And then this relaxation noise pass is a special case of this for T1 and T2, which is a common model we use for superconducting qubits, and other types of qubits also have T1 type models. And this is a local noise pass that inserts some thermal relaxation errors in your circuit based on the durations of all the gates in the circuit. So you can schedule a circuit and then apply this pass, and that will also insert noise if there's delays and other idle parts in your circuit. And you can also build your own, if you're comfortable working with transpilers, you could build your own transpiler pass to insert noise however you like. And then the most common and maybe easiest way is to just work with the noise model class in air directly. And so the noise model class is similar to this local noise transpiler pass, where it gives you an object where you can specify types of gates and then the error that should apply after that gate. And basically the same sort of transpiling happens, but it happens internally now with the air simulator when you run a circuit. So it'll take your circuit and then it will remap it to a circuit with the errors inserted on it after the gates that the noise model specifies, and then run that on the simulator. And so to work with all these, air actually, so while you can use these channel classes in the quantum info module, air has some more generalized ones that are a bit more tailored towards simulation. So in particular, there's this quantum error class, which you can use. And so quantum error is like a channel, but it's a bit more optimized for simulation. And then there's a readout error class for representing these assignment matrix-based classical readout errors. And then there's a library of sort of standard quantum errors you can use to build error objects quickly for sort of canonical errors like mixed unitary errors, depolarizing errors, amplitude damping errors, and things like that behave like operators, so you can tensor them and compose them. And so how this quantum error class works is, unlike the quantum channel ones, which are basically all defined with respect to some numpy array or a matrix, these ones represent an error as a probabilistic mixture of circuits. So you can specify any quantum circuit that's supported by the simulator. It has to contain no classical instructions, but it can contain gates, it can contain channels, and it can contain resets, for example. and you can specify a list of circuits and then a list of probabilities, and basically it will sample from these probabilities and then apply the circuit. So I could have done something like so I guess to just show the Krauss the Krauss example we did before, you could do something like this, where I already have a channel as a Krauss matrix for my error, and then so I can just say that is my circuit with probability 1, and then it will have to do the Krauss sampling for that circuit. And if I print that, what that looks like is the circuit, it's always going to be this circuit which has the error defined as an instruction. But for things like Pauli errors and mixed unitary errors, if I don't want to use a Krauss channel, I want to actually use the gates themselves, because then I can run these, say it was a Pauli error, I could still run it on a stabilizer or Clifford simulator, which doesn't support general error instructions. I can build these circuits. So for example, the circuits for individual Pauli gates or some other Clifford instruction, and add probabilities, and I get now this error object. And so that example up here, I could do directly using this Pauli error helper function, where I only have to specify the Paulis either as a Pauli operator or a string, and to get Pauli error channels. And this could have been a multi-qubit one or something if I wanted, where I can put in these things. And then you can, well, I guess I have these below. So you can compose these. So if I want to build a 2-qubit error out of 1-qubit errors, I can compose them. Note that because these are circuits, it doesn't simplify them the same way that if you're working with NumPy arrays, you would simulate them. So here it's not simple. It's not recognized that an I and an X and an X and an I is just an I, and simplified that. That would require some extra transpilation step to work with the circuits. Though this simplification, yeah. So that can be something to keep in mind when you're building these up. Same, you can tensor product them to get tensor product errors on bigger ones. And importantly, you can convert them to all the channel representations. So while you can't convert a channel to a quantum error, because it would always just be the Krauss error in a circuit, like I showed in that first example, you can convert these back, and you can do things like compute process fidelities and things with them to analyze the errors. And then for adding to a circuit, so these quantum errors now, you can just append directly to a quantum circuit, and then you can run these on the density matrix simulator or run them on the air simulator, like that. Well, I didn't have any save instructions here, so it's not returning an output. I'd have to either put measurements or a save instruction. The other case is using a noise model. So with noise models, you can either add an error to apply to all qubits of a given instruction. So here I'm saying I want this error to apply anytime there's an SX or a X gate. You could use any gates you like in your circuit, but the important thing to remember is whatever gates you put in your noise model, you should make sure the circuit you're simulating is transpiled to the basis gates you want. So say I'm using an IBM basis gates, which would be like RZ, SX, X, and CX, I would transpile to that basis gates, and I can specify the basis gates of my simulator. This is done automatically, actually, if you use a noise model, but that's something important to keep in mind. I can also add it as a specific error on certain qubits, so I could specify different errors for qubit 0 to qubit 1 and qubit 2 using the noise model. Yeah, so here it is. So one thing I could do here is something like this. So I build the noise model, I can initialize my simulator with the noise model, and then I can run it. Alternatively, I could have passed the noise model as a run option. So I can set it to none here to do an ideal simulation, or I could have set it to the noise model. But typically it's better to set it as an option of the simulator because some things happen behind the scenes that can be critically important. So, for example, say this error only applied to an SX gate. And maybe I want to change my error because X might commute with it. Where are we? Yeah, so let's do a depolarizing error with, say, a 1%. Sorry, a 1 qubit one with a 1% error. And I apply it to an SX gate. So if you where should I be doing this? There we go. So this is where you have to keep in mind of the transpilation step. So my backend here, if I look at my backend, space escape, it's got yeah, so it's, you know, X isn't in the basis gates, but a simulator still supports X. So when I run this, it's just running this and skipping the noise model. But if I transpile it now, so with this backend, now it's been transpiled to the square root X from the basis gates. And now if I run this transpiled circuit, I can see the effective noise. So it's important to make sure that you have the correct basis gates. And this is where setting the noise model to the simulator can be important, because if I just initialize a simulator, for example, it's going to have a very general set of basis gates that the simulator always supports, which is pretty much all the Terra gate library and some extra ones. And so if I initialize the simulator that way, when I transpile to the back end, you know, it's not going to change the basis gates. But when I set a noise model to the simulator, it updates the basis gates of the simulator to be some minimal set of gates for simulation. So all the custom ones like save instructions, plus the gates in the noise model. And that way, when you transpile for the backend, you're guaranteeing that you're also transpiling for the noise model you've defined here as well. And as part of building a noise model, you can specify the basis gates. So I could have said here that my basis gates were like RZ and say CX, for example, even though I wasn't adding noise to them, to include them in the basis gates. If I include X here, it would include X, and now I didn't define noise on X, so X is not going to get transpiled. So I won't get noise. So yeah, so that's an important thing to do, where it's really best to set options on the simulator object before you run the simulation rather than passing them as run options, because some internal things happen here based on that. Same with simulation method. If I wanted to do this as, say, a state vector simulation or a density matrix simulation, I can do things like that. In this case, I could also do a stabilizer simulation because I have a Clifford circuit and a Clifford noise model. Well, I think so. Oh, it didn't. Oh, it doesn't know how to transpile that as a Clifford noise model. Let me change it to an X gate. There we go. There. And yeah, so I guess at this point, I was going to ask if there's any questions for specific things people would like to see or know about that I can go through as examples.
There are no questions yet, but so as Chris asked that if anyone has any specific noise models or something that they want to ask or see, please write in the chat.
All right. have to figure out how to see the chat too. If not,
So
I
it's
guess we
okay. I
can
mean,
wrap up early.
yeah, I can.
Or
So
you
if
can ask
writing
questions through the
anything.
sheet.
Okay, so the first question is, can we have this notebook?
Yeah, sure. I mean, it's most of this is just copied from these tutorials, but yeah, I can send you the notebook too.
Okay, great. So anyone with any questions, comments, or any?
Guess not.
Yeah. Okay, so Shomodip is asking that, can you briefly describe the super operator formalism?
Sure. So I guess so the super operator. So if you specifically mean the super operator representation, so something like if I have a let's say random quantum channel on say 2 qubits, and then I write it as a super op. Oh, maybe this is let's just do it as a super operator version of a unitary, so there's less numbers. Well, I guess it still looks messed. So basically, the super operator formalism is basically like the vectorized linear algebra for working with density matrices. So if you have if you think about linear algebra for matrices and vectors, so you can have like a matrix like you know, whatever A, and a vector. This is an identity, so it's not very exciting, but you do the matrix dot the vector to update the vector. And when you're doing quantum mechanics, and you have a state vector, and well, let's say psi equals qi dot random state vector 2 op equals qi dot random unitary 2. This opt dot wait, I guess we write it like psi dot vol op is doing this, but under the hood, what this looks like is np dot op dot data. So that's a matrix with psi dot data to do linear algebra. Now, if I want to do it with a density matrix, so I can do rho is the density matrix of psi. So this is a matrix. It's defined as basically the outer product of psi, like that, which in NumPy would be np dot outer psi dot data conjugate, and that's your density matrix. Usually when we think about evolving density matrices by a unitary, it looks like this equation u dot rho dot u dagger. But what we can do is we can vectorize rho to make it a matrix, which is usually denoted with this double ket notation. And using some properties of vectorization, which are hard to write, but easy to draw pictures of, this can look like U complex conjugate O times U as a matrix acting on rho. And then this thing is basically called a super operator, which is a linear matrix that acts on the vector representation of a rho. And so if I do, so my operator, if I do the Kronecker product of that conjugate with itself. I get some matrix. And then you have to be careful about how you define vectorization, whether it's row or column. This convention is column stacking. And so what that means is the vec row equals basically np dot ravel flattens things in NumPy row, and order is f. So in NumPy, Fortran order f corresponds to column vectorization, so stacking columns. The default order C corresponds to row stacking, but I typically, in physics and a lot of the literature, we use column stacking is the general convention, so you have to specify order F. And so now I have this vector here representing my row, and then if I have this matrix that I constructed, I can do a dot product of that, and then I could reshape it back to a density matrix to view it as what it would look like as an evolved density matrix. What was it, 2, and I get some matrix. And this is essentially what's happening behind the scenes when you do super op of my op and row. So if I did row dot evolve super op, whoops, that, this is the same matrix, and this is basically how it works. It flattens the row, does standard matrix multiplication, and flattens back. And so when you're doing density matrix simulation, like in air, we never store the square density matrix. The matrix is always stored as this vectorized density matrix, and it's using this super operator convention to update different subsystems based on applying either unitaries or general channels as super operators, and updating this state vector. Updating this density matrix represented like a vector. It's not a state vector because it's not norm 1, but it is a vector. So if you relax that you can basically use a lot of the functionality you'd use for state vector simulation of just updating qubits. You could do like this. So just to demonstrate that, I could say like, where was my vec row? So I could call this a state vector. It's not going to be normalized. So if I do like is valid, it'll say false. Oh, it said true for some reason. Well, because it was a pure state, I need to do a random density matrix. So row equals qi dot random density matrix 2. Random. All right, so let's flatten this guy out. And now I get something that isn't valid. So it's not a norm 1 state because it's got these off diagonal density matrix terms. You can see it says it's 2 qubits now because vectorizing basically doubles the systems in the vector. And then if I consider this super operator here, it's not a valid operator. If I did like qi dot operator of this, it will look like a 2 qubit operator. But if I say like, is it unitary? It's not, because it, sorry, it was. Let me do qi sub equals random quantum channel. It was being too clever for me because I was using an actual unitary for the operator. There we go. So now I can hide this super operator as a non-valid, non-unitary operator. And then if I did this, I basically evolved it. And if I reshape this back, it would be the same as if I did row.evolve super operator. So that's kind of what's happening behind the scenes. You can kind of, if you have machinery for representing state vectors and evolving them, you can use that same machinery to do vectorized super operator simulation by just ignoring the fact that it's not a valid state and the operators aren't unitary, but it's still just the same linear algebra. And so that's basically a computational trick to do this.
Okay, so Shomodeep saying that it's fantastic, it's crystal clear. And Kosturi has a question that how to add 1 and 2 qubit gate calibration errors.
Yeah, so I mean, for that, the hard thing is figuring out what the errors you want to add are. So if you have a model for the error, so maybe you do like quantum process tomography or some special characterization error to learn what your gate is. So what you can do is, say I don't know what to do for a good example for this, but well, I can just use a random one, for example. So, this isn't very realistic, but say I maybe okay, let's just do something that's not realistic for a calibration error, but we'll show some of the tools you could do. So say I had I don't know, a 1% depolarizing error on 2 qubits. So let's ignore that for now. And say I had a C0 gate. And then say my noisy gate is represented by like my ideal gate by some error. But say I don't know what this error is, I just know what the ideal gate is. And you have this noisy gate, which you say you get it from I'll do it as a super op, but you could do, well, let's say a Choi matrix. So say I could have done process tomography of a C0 gate, for example, and I recover some description of the gate. Maybe you do gate set tomography, maybe you do some other characterization method, but the point is you have some model for your noisy gate of your system. So for example, something like this, and you have a model for what the ideal gate should have been, so a CX gate. So if I have the noisy gate, what I can then do is, if I have it as one of these operators, I can then basically dot product it with the inverse of the ideal gate. And now I get just the gate error term, whatever that is. And in this case, gate error, should be the original error I started with in a different form. But if, say, this was unknown, and a calibration error is typically a coherent error, so it might be like a misrotation or something like that, then, but it's over the effect of some like pulse for the whole gate, so it might not neatly fit into this model of like some canonical rotate. It might be a rotation about a weird axis, include a bit of T1 and T2 and other things. So if you just characterize the full error channel of your noisy gate and then multiply it by the inverse of that gate, you get a model for a channel which is this error. So I'm saying that my like U noise equals U ideal dot E error, so this error channel. And then I learn U noise, and then that means that like U ideal inverse dot U noise equals E error. So I use that equation to recover the error. And then once I have this, I can then now make for example, a noise model. And then I can say add quantum error of this gate error to the gate that I characterized, and say this was on qubit 1 or something. Oh, why isn't this working? well, maybe that, let's, yeah, I think I'm using the syntax wrong, but whoops, and of course there's a 2-qubit gate. Yeah, so basically once you get these errors, you could then build up a noise model for the gates that you characterized and put in all the custom errors you want, and now you have a noise model that can represent, say, calibration errors for the gates in your gate set. And if you go through the tutorials, there's an example, I think. I can't click it because of the WebEx things. Tutorials. So there's, if say you're trying to simulate a system that isn't an IBM one, you could add like this is an example of adding them to custom gates. So I could say like I have an iSwap gate in this example and I want to add a custom error to it. But if it's one of the IBM ones, it would typically be a C naught or a square root X. And so you can just add them like this for the specific qubits you want. The hard part is figuring out the error of the noisy gate, I guess, with however much accuracy you use. So typical things would be like gate set tomography or quantum process tomography you could use for that.
I have just one follow-up question here. So once you have this noisy gate, which you kind of took as like this controlled NOT gate with the depolarizing thing, and you have taken the Choi formulation here, but if I don't take the Choi formulation here, can I apply it directly on a quantum circuit and call it my custom gate or something?
I mean, you could still apply this Choi directly to a circuit, but it's only going to work on a simulator at that point.
Yeah,
it won't
right.
work on a real device. So I could have just, yeah, I could have just replaced all my CX gates with this noisy CX gate directly in a circuit and run a simulation, and that would be perfectly valid and work. If you want to preserve the original circuit so you could run it on a real device, then that's where it's good to convert to a noise model.
Mm-hmm. Yeah.
But yeah. So I could have done like, quantum circuit, done a Hadamard, and then just added this like not noise gate as my CX gate, for example, directly, and get some noisy, circuit. You could also, if you wanted for simulation, that's where you could use these things like the local noise pass in air. You could write a noise pass that just replaces all CX gates with this noisy gate, or you could write a pass that appends them with the gate error, and that's kind of up to you what you want to do there.
Yeah, got it.
I should say one thing we're working on in Qiskit at the moment is a better pulse simulator using this new package, Qiskit Dynamics. And when that's released, that's something you could do like this as well. You could, if you have a model for your Hamiltonian or your Lindblad for your system, you could do a pulse level simulation of a gate to get, say, the super operator or noisy unitary for the gate, and then do this inverse trick to then get an error model that you can put in the circuit simulation, because circuit simulation is much faster than pulse simulation, to use, say, like some more sophisticated noise model in your circuit simulation. And that's fine if you can do some sort of calculation to get the noise error. But if you're just using a real device, you have to use some QCVV procedure like tomography or similar to get it.
Yeah. Okay, great. So any more questions, anyone? If not, then I guess we can thank Chris for this wonderful presentation. And I at least got to learn a lot. I knew some of these parts, but still I got to learn many other parts also. And I hope all of you did. So thank you so much for giving this wonderful talk. Please
Thanks.
kindly share this notebook.
Sure. I'll send it to you, Rijit, and you can share as needed.
Yes, yes, sure.
All right.
Okay, so thank you. And to all the participants, we'll again see you tomorrow for our last session of this Fall Fest. And tomorrow will be on quantum machine learning. So, okay. Okay, then. Good night for today. I'll just stop recording.